Okay. Good evening, everyone. I hope I don't have to introduce myself too long. I'm Radu Ștefan. Probably some of you were at my course in signals and systems and/or feedback control systems in the second year. For many years, I have worked together with Tudor and with another colleague, which unfortunately is not anymore with the faculty, Alexandru Țiglea, on this course. And the outcome of this work during the years are the slides that you have now, and on which we made or we constructed our talk at this course. So I will just start to point out a few things which I think are important. First of all, let's go a little back to stability concepts. If you remember from our first course and also on signals and systems, the concept of stability was there related to an input-output condition. So stability, when we had a transfer function, was or a convolution system or an input-output system, generally speaking, was just a condition that for every bounded input, the output of the system should be as well bounded. Well, you see here at the Lyapunov stability concept, our stability concept does not go to look for inputs and outputs and boundedness of signals, but rather to define the stability as the property of a certain particular solution of the system of differential equations, which in our case is of the form 6. It's an autonomous system, right? So the difference of the concepts is quite consistent. Lyapunov and the stability in sense of Lyapunov is stability with respect to a reference solution. Now, you have easily seen that with the change of coordinates, with a simple translation, we can refer to any reference solution, and this is also an important point which I wanted to emphasize. So whatever reference solution I take, if I make this translation written in Formula 7, we can go back to the stability of the trivial solution, of the solution x of t identical 0. And from now on, starting with these definitions, all our discussion went towards stability with respect to the origin. But keep this in mind, please. The origin, yes, it's a point in the Euclidean space of dimension n, but it's also, for us in this case, it's actually the zero solution. It's a reference solution, right? Of course, we translated the system and automatically the equilibrium point 0 became the reference solution, because if I take x of t equals 0, then clearly we obtain a solution of the differential equations. So this was my introduction for today. Yeah, let's have always in mind that we look at the stability of a reference solution, but we will refer in the sequel to stability also in the formulation of our exercises. Yeah, we will say investigate the stability of the origin. Yes, but remember, it's the stability with respect to the zero reference solutions. Okay, now we have passed through the, let's say, standard definition. I think everything was clear here. I'm sure Tudor has also drawn what is to be drawn. a small historical insight. And Tudor, I will ask you, did you make any computations regarding the total energy and the pendulum? Should I take this over? What do you think? Tudor left. Yeah, the question is, did you have any insight of how to get the energy function for the pendulum or not? Should I go back on this? Hey, I wait for your feedback.
I think you should go back on it.
Okay, I will then.
Okay, thank you.
Yeah, good. Right. So the idea of Lyapunov was a little bit the following, and now I will start drawing a little bit. Well, how was his idea regarding the significance of this defined Lyapunov function? Yeah. The idea was to see it as an energy function. It was the total energy of a system, and yes, what does mean that the trajectories are stable? We have seen in the equilibrium point is stable in asymptotically meaning. Yes, this is the usual meaning which we will work with, right? So the origin should behave like an attractor, and yeah, think a little bit at the pendulum, and we will go with we'll go on with the pendulum example during this talk. Think of the pendulum. Yeah, it has an equilibrium point. Now take the mechanical system. I will start drawing now. Right. Get back to the pendulum. Right. The construction we had is as follows. You have a fixed point, and to fixed point, we have a rigid beam. On this rigid beam, at one end of the rigid beam, we have a mass m, which can rotate in vertical plane, and which could also be driven by a torque without any problem. Yeah. Torque is a driving force which rotates this pendulum in the vertical The trajectory will be obviously a circle. Yeah. And we have I was not so good at drawing it for my next purpose, but just erase shortly, right? And now we have written, or we can write some equation, some motion equation. Yeah, this is not so difficult to achieve. One can assume, and this is an important assumption. We will come back to this later. Yes. Let's assume that the beam with the mass are moving into the opposite direction of the plot, right trigonometric direction. Yeah. The forces which act on this mass are, on one hand, the tangential component of the weight, and on the other hand, we could also imagine that if you go in this direction, so the tangential speed is like that. This is g. This is, I would g theta, where theta is this angle, right? You can also assume that there is a friction force. It's a friction force. I did not assume that we have a friction force here, but I assume that we have a friction force. We will assume that we have a friction force with the air. There is also here a friction force, also opposite to the speed, right? G theta is obviously mg sinus theta. Yeah, we retrieve the same, this is theta as well. Yeah. We have the tangent to the circle here. And the friction force, as I said, is proportional to the speed. So it should have a constant proportion with the tangential speed. But the tangential speed is the rotational speed omega multiplied by the radius, which in this case, the second law of dynamics writes in this case as follows. I will go directly to the notation of the derivatives. So theta is the angle. Dot theta omega is the angular speed. And the angular acceleration is theta double dot. This is usually multiplied. And the second law of dynamics for rotational movements works the same. So we have g multiplied by alpha equals the two moments minus g theta by L. These are opposing to the movement. The movement is given by the torque, and these two are opposing to the movement. That's not right. I will so g alpha minus g theta multiplied minus friction force plus, of course, the driving force dc. So we will end up with a differential equation, and finally with the system equation you have written already. Yes, but don't forget about the significance. So now we have, for this system, one can calculate g is the moment of inertia of this system. And one can prove, don't ask me, it comes from the mechanic. One can prove in this case that j is m L square multiplied by theta derived 2 times equals mg sinus theta multiplied by L minus k theta dot L multiplied once again by L plus dc. You know, you end up with a differential equation. Right? If I will divide now everything by this vector, we get double dot theta equals minus g over L sinus theta minus k over m theta plus 1 over ml squared. And this is a forced differential equation of second. You can have, this is the control, is the force you put here inside. Assume now that you don't. Assume that c equals 0 and make the usual trick we do to transform a higher order differential equation into a system of equations, but of first order. What is the trick? Do you remember? What are we doing? Get from one equation of second order to a system of two equations, but of first order. What was the trick to do that? We did it also in Singleton systems in a couple of examples. Do you remember? No. We took the position to be one variable. So x1 is the position, x2 is the speed. Very common to do that. Not only in mechanical system, but also in electrical system. And then one can immediately set x1 dot equals x2. First, x dot 2 is actually double dot. Then we can copy this equation. And this equation is minus j over L. That's sinus x1 minus k over. I have let's say forgotten about the control. We assume that the control is 0. So have in this case an autonomous system. The situation we are studying. Dot equals f of x. Of course, f has two components. F1 depending on x1 and x2, which is Now, let's go back to our intuition, which comes from physics or just from the common sense. Can you look at this system and define an equilibrium? It's an equilibrium encountered earlier in physics. We had in physics, or we talked about several types of equilibrium. Do you remember? I mean, what is now an equilibrium for this type of a non-linear system? Or let's put it this way. If I say that the origin corresponds to a trivial zero solution, what does this mean? I have a system, what we have written in the slide. I have a system, x dot equals f, and we say f is 0 is 0, right? And then we say x depending on the identical trivial solution. What does this really do? Look at this equation. If I take the trivial solution, x equals 0, will this be a solution? If I initialize the system in the origin, x1, 0, will it stay there or not? What would be the solution? If we take the initial condition, take 1 of 0 plug them in here. What will we get out? What will be the solution? What will it be? How much would we have this one of these? Think a little bit. X2 is 0. Derivative x1 is 0. So x1 is the derivative of a signal or a function is 0. How is the function? It's a constant one. Okay? So x1 will be constant, but the initial condition is 0. So x1 will be 0. x1 0, sinus x1 0. 0. X dot 2, the derivative of x2 is also 0. So x2 is also constant. x2 will be 0 as well. Now, notice this f of 0. What we have here, f of 0 is 0. I don't have to write it because you have there on the right. Good. So,
Please excuse me to interrupt. We can't hear you very well.
why is that?
I don't know. Now it seems to be better. But
Now
it's like really with low volume.
I also suggest you turn off the camera for better connection.
Tudor, I will do that. Just a second. You know what's a little bit strange? A little bit strange is the fact that I never had. Maybe it's the time of the day, you know, because the other course I give it's on Friday starting with 11, and probably the network is much more loaded now. Is it better now?
Yes, it is better.
Okay, but you should have pointed this out earlier, not letting me go on and on like that. Okay, so I'm coming back. Which is the point, the equilibrium point, which is corresponding physically to the origin, or to the trivial solution x equals, or x identical 0, which I have written here. Which is the physical point corresponding to that? Can you tell me? So where is the point in which I place the beam and the mass, yeah, the ball, and the system remains there? It doesn't move. I don't have any torque. the torque again, the torque is 0. We get rid of this. So which is the point which corresponds to angle 0 and to speed 0? Which is the point from, I mean, physical point of view? Yeah. Which is that point?
In
On
the
On the
middle.
vertical axis.
Yes, is
Yeah.
on the vertical x here in the middle. That's the point. If we take the ball and the beam and we place it there, attention, with 0 speed, so angle is 0, speed is 0, it will remain there. Okay. But what happens if we take it out from this equilibrium and we will let it on a free evolution, no torque? What happens? We have friction. We don't have friction here, but we have friction with the air. What will happen eventually?
It will come back to the initial point.
Yeah, it will oscillate around the equilibrium point and it will be driven at the equilibrium point. Why is this happening? Because at the moment you have taken it from the equilibrium point, right? What did we do? We confirmed to the ball some potential energy. Just look here. Sorry. Yeah, just look here. You confirmed some potential energy. Yeah, if this is the place of lowest energy, then this distance denoted by h, yeah, confirmed to the ball some potential energy. Yeah, what would that be? This component of the energy will be mgh. Yeah, you could also push it a little bit. The direction doesn't matter. So you could also convert to it also initially some kinetic energy, which is 1/2 mv squared, right? And this would be the total energy of the system. So the ball will oscillate until it will what? It will dissipate the energy into the friction. And this is precisely the idea of Lyapunov when defining Lyapunov functions. Yeah, you have functions which take always positive value and which decrease along the trajectories. So the energy becomes smaller and smaller once the system evaluates, yeah, from on a given trajectory, yeah, which is perfectly defined by the initial conditions, right? By the initial angle and the initial speed. Do we all got this intuition regarding the energy which is dissipated along the trajectories, along these oscillations? Okay. Do we have some other equilibrium points? What do you think? Are there any other equilibrium points? Except this one. I leave the drawing as it is. And just until you think, I will just compute this energy and I will get some more space here. Tell me. Is this the only equilibrium point of the system?
No.
We have another one. Which is this other one?
Yep. 180 degrees opposed to this one.
I cannot draw it now because I just took the figure as it is in order to have a little bit more space down. But there is also the equilibrium point, and you can follow me, which comes in vertical position, but 180 degrees far from this one. I mean, when theta is 180, we'll have another equilibrium point. Okay, can we look at this other equilibrium point from mathematical point of view? What do you think? I mean, it's clear for all of us. if we take the ball and the beam and we put it exactly in vertical position, but upwards, not downwards, we will have the system at rest. It will not move from there. Of course, if we make an infinitesimal perturbation, it will move from there and it will not get back, because this was the point of maximum energy. Yeah, but if we don't do that, it will stay there. Which means, what does it mean? Yeah, it's fixed. It means that we will have a solution. X1 will not be 0 anymore. X1 will be how much? I will put the radian notation. It will be pi, right? X2 will be in any circumstances 0 again. But have a look at the equation. Will we get f depending on pi and on 0 also 0? Well, clear. X2 is 0, so this is 0. X2 is 0. And then if we want to equal the right-hand side of the second equation by 0, we have just to put sinus of x1 being 0. So every solution to sinus x1 equals 0 will define an equilibrium point. Now, from physical point of view, we only have 2. But from mathematical point of view, we have an infinity. Why is that? This is because, for sure, sinus x1 has an infinity of solution. Yeah? What is the solution of sinus x1 equals 0? How much is x1 from this one?
K pi with K integer.
K pi with K integer. Right, thank you very much. So it's an infinity of equilibrium point. Note that, please. Yeah. So I can add here, actually, yeah, these are all equilibrium points of the system. I will take this out from here. Yeah, and they will be constant solution. So this is actually all. These are actually all equilibrium points of the system. K pi and 0 with K any integer. Very fine. Yeah. From physical point of view, we have only 2. Why? Because I have pi. Then, if the rotation continues, I have 2 pi. Yeah. 2 pi 0, 0, 0, and so on and so forth. You understand? Or if I go backwards, I will have minus pi, minus 2 pi, and so on and so forth. Yeah. So I think this is clear. And we come now with the very clear statement about the nature of these 2 equilibriums. So if we look at the equilibrium, let's say downwards, that from the bottom, if we perturb a little bit, then we will have some oscillations, but eventually the ball will retrieve the equilibrium point. So we will have what, with respect to the reference solution 0, 0 or 2 pi 0, what will we have there? But let's go to the solution 0, 0. What will we have? What is the property? If I perturb a little bit, then I retrieve closely the solution, the reference solution,
Stable.
which is 0, 0. So we will have stability. We know from physics that this point is a stable, this equilibrium is a stable equilibrium. Yeah. Whenever I perturb a little bit, yeah, of course I will not push it in upwards. No, if I perturb a little bit, it will oscillate somehow, and then we will have again the 0, 0, or the equilibrium point achieved. On the contrary, upwards, at the smallest perturbation, we lose the equilibrium. And this was called an unstable equilibrium. And with the Lyapunov theory regarding stability, we'll have a short, immediate, and very, very clear argument why one equilibrium is, or all equilibrium upwards are unstable and all equilibrium downwards are of course stable. Let me perform this calculation here now, right? If you look at H, so this is mg. If you look at H, what is H? H is the difference between L, the entire length, and this segment, right? What is this segment? This segment is just L cosine theta. So I have here L minus L cosine theta plus 1/2 m. V, we have defined it already. V is dot theta squared, and we get L squared. And the expression of this is if we get out from the, let me put it in red, why not? If we get out ml squared from the expression, we will obtain what we will obtain here. I will start with this one first. 1/2 theta dot squared plus g over L. I hope I have still some place. 1 minus cosine theta. And this is the expression of the total energy of the function. Okay, let's get back to our slides. Okay. Sorry. Yeah. The pendulum. This is the total energy of the pendulum, and it works like a Lyapunov function. It's, I would say, one of the best examples to really understand it. It has the significance of energy, and if energy decreases along the trajectories, then we will reach, of course, the origin as an attractor, and we will be able to say, yeah, this point is asymptotically stable. I will come back to the calculation a little bit later, and on this slide, as well. Let us recall the Lyapunov theorem. Yeah, right. So if we find, let's have always the assumption checked. We need f of 0 equals 0. So the origin has to be an equilibrium point of the system, right? And if we find a Lyapunov function, which has to have actually, from, let's say, a candidate point of view, three important properties. Continuously differentiable on a neighborhood of the origin, 0 in 0, so 0 at the origin, and positive definite on this neighborhood. This is always our candidate, and then we will try to prove that it decreases along the trajectories. How? We will look at its derivative, and we will try to prove that it's negative definite, which means strictly lower than 0, so strictly decreasing, or just non-positive definite along the trajectories, which means that it's not strictly decreasing. It decreases, but not strictly. And on these two situations, we get the right conclusions. We have simple stability if the derivative is non-positive, and we have asymptotic stability if V is negative definite. Let's make the calculations for our pendulum, right? Let's do this. Let's do this calculation. Yeah. So take the energy. I have taken the ml squared term out because it's not it's not influencing sign and things like that at all. Okay, look now. Yeah, these functions are analytic, so continuously differentiable. V in 0 is 0, right? Cosine in 0 is 1. 1 minus 1, 0, 0. And we take a strip, yeah, around the origin minus pi, where we compute the derivatives along the trajectories. A very, very important of the theorem is that we have to prove this non-positive definiteness or negative definiteness on a neighborhood of the origin. And we are allowed, or even, let's say, keen to find the right neighborhood of the origin. So the property and the theorem is a local one. Yes, sometimes we want global stability, but that's another story. But usually when we want stability or asymptotic stability, it's a property which goes local on the equilibrium point. V can be as small as necessary if we get the derivative negative definite on D. It's absolutely no problem on that. No problem on that. Okay, so let's get to the derivative, right? We have to derive V along the trajectories, and we have seen. I will come back to many calculations today. Yeah, what was the formula for the derivative? Well, not difficult to see. You want to derive V with respect to the time, and we take then the partial derivative with respect to x, and we take the derivative of x with respect to time. Yeah, and then you get this formula. Yeah, it's the sum between the partial derivative of V with respect to every state multiplied by the derivative of that state. And if you put it, if we notice that x dot I is actually fi of x, then you end up with the formula 8. This remark is very important. Yeah, the derivative depends on the point and not on the time. This is because we have here a dynamical system which is defined, but that's also a thing. I don't know if Tudor went into the details at the right time, but yes, this type of equations define dynamical systems, right? And trajectories can be retrieved going from one time moment to the other moment. Okay, let's do these calculations. So we have first the derivative of V with respect to x1. This term does not contain x1. We make the derivative with respect to cosine. Cosine derived is minus sine, but with the minus from here, we get just sinus of x1 multiplied by g of L. And of course, we multiply by the derivative of x1. The derivative of V with respect to x2, yeah, this is a term which contains only x1. So it will be 2 multiplied by 1 over 2 x2. So obviously it will be x2. And if we calculate things here, we will end up with this expression. Why? It's easy. X dot 1 is x2. So we obtain here g over x2 sinus x1. Well, while x2 in x2 dot, and I will go now back to our formulas in the notes. Yeah, look, it's minus g over L sinus x1 minus k over m x2, and once we have multiplied all this element with x2, we'll get minus g over L x2 sinus x1, which cancels with the first element, and then we get minus km x2 squared. That's all. is very easy to see that. And we ended up with a derivative which is non-positive definite. So the origin is a stable equilibrium point. Yeah. But the question comes, our intuition is obviously showing us that the origin is asymptotically stable. It attracts the trajectories once you perturb a little bit from the origin. Yeah, after a while, you will get back to the origin. So the physical intuition clearly shows that the origin and all the points of the type 2 pi 0 are asymptotically stable equilibrium points. Yeah, what to do about it? What to do about it? Well, actually, there are two possibilities of reasoning from here on. Yeah, one possibility of reasoning is this one. Well, W is negative definite because we can find points x1s for which the function is 0, but yeah, we cannot put it strictly than 0, right? I mean, if I take any point where x2 is 0, x1 can be indefinite. We will always have here W equal to 0. Yeah. But now comes into place, let's say, or as I said, another way of reasoning. Okay, but what? The question is, will the energy of the system still decrease at points where W is 0? I mean, yes, when it's 0, it will not decrease strictly. But can we prove that eventually it decreases? And we look at this set, denoted here by calligraphic N. Yeah. Let's look at the set where W is 0. Yeah. Don't forget, we have restricted our analysis in a strip around the origin. I will go back on the drawings with the phase portrait of the system. Good. So we are analyzing what happens only in this strip. Well, x2 is 0. So obviously, x1 has to be a constant, right? x2 is 0, x1 has to be a constant. Yeah. But since the derivative of x2 is also 0, because x2 is constant, then obviously sinus of x1 must be 0. Look at the equations once again. Yeah, we're in the following situation. x2 is 0. So x1 dot is 0. x1 is constant. On the other hand, x2 is 0. x1 is constant. It has a value, let's say x1 star. But the derivative of x2 is also 0 because x2 is constant. So the only possibility is at points which make W equal to 0 have to satisfy sinus of x1 equals 0. It is how it is. It's a simple derivation of condition. Okay, but where does it happen with x1 in this interval minus 5 pi that W of x equals 0, meaning sine of x equals 0? Only at the origin. Aha. So basically, our fear that W or that V, better said, V will not decrease along the trajectories is actually removed by the fact that if W equals 0, meaning that we'll have no strict decrease of V, happens only on the trivial trajectory, only on precisely on the trajectory x1 equals 0, x2 equals 0. Yeah, but this means that v strictly decreases along any other non-trivial trajectory. Hence, the origin is an asymptotically stable equilibrium point. This is one way of reasoning, right? Before getting to the break, we will formulate after the break a corollary regarding this type of reasoning. Getting back to our Lyapunov theorem, yeah, look what it's written here. If there exists, so we just took a Lyapunov candidate here. It was this function as a Lyapunov candidate, right? But what happens? What happens? Yeah, if we would go for another function, and I will open this discussion immediately after the break. Shall we meet back in 13 minutes, 7:05? Is this okay? Because I stop recording at this point. Yeah.